Hello, everyone. I'm trying to record this video and using a new program to do it, so it might not work out perfectly. But what I'm trying to talk to you today about is oxidation numbers. And I know we've gone over this before, but since we haven't talked or met in about 3 weeks, I thought we should go over this again so everybody has a good idea of what this is about. And it'd be a good starting point. Um, so I wanted to go over this first, and then later on go over percent composition again, and then talk about something new. Okay. So today, what I want to talk about is oxidation numbers. So what are oxidation numbers? Oxidation numbers are in order for to indicate the general distribution of electrons among the bonded atoms in the molecular compound or polyatomic ion. That is called oxidation number. It's also known as oxidation state. Okay. There are several rules that govern the oxidation numbers. And once again, we've talked about this, but I want to go over them again. So anything that has any pure element has oxidation number of zero. So for example, oxygen 2, O2, is oxidation number of zero. More electronegative element in a binary compound is assigned the equal number of the negative charge. It will appear as an anion. We've talked about that before. I'm going to explain that here in a second. Fluorine always has an oxidation number one of a -1. Oxygen almost always has an oxidation number of a -2. Hydrogen can have an oxidation number of a +1 or -1, depending on where it is in the compound. And we'll talk about that more here in a second. The algebraic sum of oxidation numbers of all atoms in a neutral compound is equal to 0. The algebraic sum of oxidation numbers of all atoms in a polyatomic anion or polyatomic ion is equal to the charge of the ion. We'll talk about that here more in a second. And then right here, the monatomic ion has an oxidation number equal to the charge of the ion. For example, the ions Na plus, Ca plus 2, and Cl negative all have oxidation numbers of +1, +2, -1, respectively. So, what does all that mean? All that is the theory, but how do you actually apply it, right? So, once again, I wanted to work these sample problems right here to show you how to do this. So, the first one is uranium hexafluoride. Let me get that in frame. Okay. So you have to use periodic table like this one that has ions on it. I've given you this before, right? Um, Fluorine is right here, has a -1 charge, but that's also the oxidation state. One of the rules says that the negative anions of the oxidation states and the charges match up. Okay, so if this is the negative side, this has to be the positive side. Okay, so what you do is you take this -1 times 6, because you have 6 of them, and you have a -6 on this side right here. If you have a -6 on this side, then you have to have a +6 on this side. Okay, you only have one uranium atom, so that means the oxidation number for uranium is a +6. The oxidation for fluorine is -1. Okay, that's your answer. All right, let's do another one. Another example. Okay, so here you start with the negative first. Okay, the negative is going to be the most consistent one. So for oxygen, right down here, it's going to be a -2. Okay, the oxidation state and the anion charge are the same thing in terms of the number. Okay, so -2 times 4, excuse me, is a -8. One of the rules that we just went over says that if hydrogen's on the left side, it's going to be a +1. So 1 times 2 is +2. This has to equal a 0. So what's the difference, right? So if you owe somebody